So another example of a rational expression in our integrand that's going to require a partial fraction decomposition. This one's a little bit different, however, because you'll notice that we do not have linear factors in the denominator. And in fact, we have the square of a squared factor. So this corresponds to case 4 in your partial fraction decomposition handout. So what we want to do is set it up, since we don't have linear factors. When we break this guy down, we're going to have ax plus b as our numerator with a denominator of x squared plus 1, and then we raise the power of the denominator and we have another set of constants cx plus d in the second part of our partial fraction decomposition. So just like before, I am going to clear the fractions. This time the common denominator is x squared plus 1 squared. So I'll multiply everybody by that, which will give me 2x cubed equals ax plus b quantity times x squared plus 1 quantity, and then the fraction cleared for cx plus d, so he's there by himself. I'm going to go ahead with this ax plus b x squared plus 1 term and distribute, and that's going to give me 2x cubed equals ax cubed plus bx squared plus ax plus b, and then that cx plus d guy comes down. So I'm going to try and equate coefficients again. So to do that, I have to group by degree. And you'll notice that also on the left, I'm missing the squared coefficient, the linear coefficient, and the constant coefficient. So I went ahead and added those in on the left as zeros, and then I grouped together my remaining coefficients. So ax cubed didn't have any partners, bx squared didn't have any partners. I grouped together ax plus cx, and I grouped together the constants b plus d. So I'm getting ready to equate, so I had to factor over for the linear terms out the a plus c, and then I'm going to set up a system of equations and use some algebra to try and solve for a, b, c, and d. So notice that the coefficient on the left for the cubic term matches with a on the right. And notice that the coefficient of 0 for the quadratic term matches with b on the right. The coefficient of 0 for the linear term matches with a plus c on the right. And the 0 constant on the left matches with b plus d on the right. So when I set up that system of equations, over here, right away, I know that 2 equals a and 0 equals b. But then I have 0 equals a plus c and 0 equals b plus d as well to solve. So I went over to 0 equals a plus c and put in 2 for a and solved for c equals negative 2. Excuse me. And then 0 equals b plus d. I plugged in 0 for b, and I got 0 for d. So now that I know my coefficients a, b, c, and d, I can go back to my integral and solve it. All right. So if I go back to my integral, notice the setup, that case 4 partial fraction decomposition. And I'm going to rewrite my single rational expression as the sum of 2 rational expressions. I plugged in the coefficients I just solved for, a, b, c, and d. And this time I don't have quite a straightforward integration, but I am going to have to do a u substitution in these two different parts. So for my first one, I let u be the denominator, x squared plus 1, and then I did have 2x dx right here, which is kind of nice, for my du. I'm also using the inner function in the denominator here, x squared plus 1. And I do have the 2x dx, I just have to keep an eye on this negative guy here. So now that I have my u sub set up, I can go ahead and start the integration. So when I simplify it now, my new integral looks like 1 over u du plus the integral of negative 1 over u squared du. Excuse me. So on the left I get natural log of u, and on the right I get a negative from the coefficient and then a negative 1 over u from the power rule. So my last step is just to plug in u, x squared plus 1, and my constant c. Now you'll notice from this step to this step I dropped my absolute value bars. The reason I did that is because I know that x squared plus 1 is always positive. X squared is always positive, and I'm adding a positive to it. Now if you leave the absolute value bars there, it's not wrong. It's just that I'm confident that this is always going to be a positive number, so they're just not necessary.